Welcome to Your Math Explained, where we make math simple and clear. My name's Angela. Up to now, we've talked about limits using phrases like x gets close to a and f of x gets close to L. That intuition is powerful, but it's also vague. Today, we will answer a very important question. What does gets close actually mean precisely? Calculus doesn't rely on hand-waving. If we want to prove limits rigorously, we need a definition that leaves no ambiguity. That's exactly what the Epsilon-Delta definition of a limit does. Now, before we dive in, if you haven't subscribed to the channel yet, make sure you do that first so you don't miss out on new weekly content. The precise definition of a limit says that the limit as x approaches a for a function f of x is equal to L if, for every epsilon that is greater than 0, there must exist a delta that is greater than 0, such that this statement here is true. Now, if this looks like gobbledygook to you, don't worry. We're going to demonstrate this first with a diagram, and then we're going to take a look at a couple of examples. So first, let's go ahead and draw a diagram. We have our x and y axes. And then let's say we have some random function f of x. So let's say this is our function f of x. Now let's call this value here our a. And therefore, this value here is going to be our L, since the limit as x approaches a for f of x is equal to L. So now epsilon controls how close we want the output to be to L. So you can think of it as a band around L. So which means this here would be L plus epsilon, and this here would be L minus epsilon. So this band dictates how close we are to the value L. It gives you plus minus epsilon away from that value. Now delta is going to control how close we are to A. So in this case, this would be A plus delta, and this here would be A minus delta. And then the band here shows how close we are to the A value. So in this particular diagram, we've shown that if we've picked this particular epsilon value, then by selecting this delta value, we would have x minus a is less than delta, and that is going to ensure that the absolute value of f of x minus L is within that epsilon band. So in essence, you can almost think of this as a game. In order for the limit to exist, it doesn't matter what value you select for epsilon, we must be able to come up with a value for delta so that this is true. And this delta is going to be a value based on epsilon, and we get to construct it. So let's take a look at what that means through our first example. So here we want to use the Epsilon-Delta definition to prove this limit. Now we know that we can use direct substitution here, but let's see how we can actually do it with this precise definition. So here, let's go ahead and write down our function f of x. That is going to be 3x plus 1. And then our L here is 7. And then our a here is 2. So the precise definition says that for every epsilon, there must exist a delta such that x minus a, which is 2, is less than delta, implies that the absolute value of f of x, which is 3x plus 1, minus the L value, which is 7, must be less than epsilon. And it is up to us to find this specific delta value. So generally, what you want to do is you want to start here, and then you want to solve for the absolute value of x minus a. So I have it in quotes, is because we're not actually solving for it. You can think of it as isolating it, because that way we can go ahead and construct a delta that's going to make this statement true. So therefore, we start with the absolute value of our function f of x minus our limit, which is 7. And this is equal to absolute value of 3x minus 6. And we know we can factor out a 3 here, so this would be 3 times the absolute value of x minus 2. And we know that this is going to be less than the epsilon value. So here we can see that we have the absolute value of x minus 2 that we wanted to solve for. So let's go ahead and isolate that. So this means we get absolute value of x minus 2 is less than epsilon divided by 3. So therefore, we can now choose our delta and let it be equal to epsilon over 3. And this is because if we choose that to be our delta, then that means the absolute value of x minus 2 is going to be less than epsilon over 3, and that implies that 3x plus 1, which is our function, minus the limit, which is 7, is going to be less than epsilon. So in other words, this means it doesn't matter which epsilon value you choose. If I set my delta value to be epsilon divided by 3, then this statement is going to be true. So for example, if we pick epsilon to be 0.1, then delta is going to be 0.1 divided by 3. So this means that for all the values where the absolute value of x minus 2 is less than 0.1 divided by 3, the absolute value of 3x plus 1 minus 7 is going to be less than 0.1. And so therefore, we have now proven this limit. Next, we're going to take a look at a quadratic limit, and this one's going to be a little bit tougher. So again, let's start by writing what we know. So our function f of x here is x squared. Our L here is 1, and our a here is also 1. So this tells us that we want to start with the absolute value of f of x minus L, and that is going to be less than epsilon. And then we want to solve for x minus 8. So we want to solve for the absolute value of x minus 1. And that is going to allow us to construct a delta that will satisfy the epsilon-delta definition. Okay, so let's take a look at the absolute value of x squared minus 1. So we know that this is equal to x minus 1 times x plus 1. And here we're able to split this up into two absolute values. So this is the absolute value of x minus 1 times the absolute value of x plus 1. So right now what we have is the absolute value of x minus 1 times the absolute value of x plus 1 is less than our epsilon value. So notice how we want to solve for x minus 1. And we have that right over here. But we have this extra absolute value of x plus 1 term that we want to get rid of. But our delta term can't depend on x. So in a way, we want to replace this absolute value of x plus 1 with a constant term. Okay, so how are we going to do that? Now this part might seem a little bit magical. What we're going to do is we're going to arbitrarily assume that our delta is less than or equal to 1. And the reason that we can make this assumption is, in general, once we find a delta that works, all smaller values of delta will also work because they're more stringent. And again, note that we just arbitrarily assume that delta is less than or equal to 1. You can pick any other number you want. You can pick 0.1, you can pick 2, you can pick 3. It doesn't matter. So if we assume delta to be less than or equal to 1, then what's going to happen is that the absolute value of x minus 1 is less than delta, which is less than or equal to 1, implies that x minus 1 must be less than 1, and it must be greater than negative 1, which implies that x must be greater than 0 and less than 2. So if that's the case, then that means the absolute value of x plus 1 must be in between 1 and 3. So we don't care about the greater than 1 part. What we only really care about is that the absolute value of x plus 1 must be less than 3. Because if that's the case, then that means the absolute value of x minus 1 times the absolute value of x plus 1 must be less than the absolute value of x minus 1 times 3, since we know that the absolute value of x plus 1 is less than 3. And we know that this is less than epsilon. And now we can go ahead and solve for our x minus 1. So this means that absolute value of x minus 1 must be less than epsilon over 3. So now the last part is just for us to choose our delta. So we're going to choose our delta to be equal to, and this is going to be the minimum between 1 and epsilon over 3. The reason that we're picking the minimum is that this guarantees that both assumptions that we have made about delta in the course of this proof are taken into account simultaneously. So by choosing this delta, we have guaranteed that the absolute value of x minus 1 less than delta implies the absolute value of our function f of x, which is x squared, minus the L value, which is 1, must be less than epsilon. And thus, the limit has been proven. And now let's do a quick recap of what we covered in this video. We saw that the actual definition of the limit requires a precise definition, not just intuition alone. And in this epsilon-delta definition, epsilon controls the output closeness, whereas delta controls the input closeness. And the goal of these proofs is to link the absolute value of f of x minus L to the absolute value of x minus A. In the two examples that we went through, we saw that linear limits are pretty straightforward, but the nonlinear ones require some bounding techniques. And this precise definition is what justifies the direct substitution property. And now it is your turn to give this a try. Can you use the epsilon-delta definition to prove this limit here? Don't forget to leave your answer in the comments below and let us know what other calculus topics you'd like to see in the future. That's it for this video. If you found it helpful, remember to hit that like and subscribe. And if there's a topic you'd like us to cover, make sure to drop it in the comments.